Hi, this is Gary from Ether Security Lab, and in this video we're gonna go through the fourth challenge of the Flare 2019 challenges. Fair warning, the solution we will walk through is not the simplest solution. I intentionally left some of my mistakes in it, so you can see how I overcame those mistakes. If you haven't seen my walkthroughs about the previous challenges, you can find them in the description. So this challenge was called the DNS chess. That's a hint already that there might be something to do with DNS. When you download the challenge, you get a couple of files. There was a capture.pcap, chess UI, which is a Linux executable, and of course the message.txt, and the chessai.so, which is a shared object, so basically a Linux library. If you look into the message, it says, some suspicious network traffic led us to this unauthorized chess program running on an Ubuntu desktop. This appears to be the work of a cyberspace computer hacker. You will need to make the right moves to solve this one. Good luck. So the first thing that I did was to look into the pcap file. You can open it in Wireshark. When you start to analyze the pcap file, you can see that it contains only DNS traffic, which is not a surprise because it was called DNS chess. If you look into the hostnames that are being resolved, they look like rook-c3-c6.gameofthrones.flareon.com. So you could see that it goes like chess figure, then probably coordinates of the chessboard, and then just gameofthrones.flareon.com. So the hostname basically says which figure should step from which field to where. And since it's DNS, the response is an IP address. There are all kinds of IP addresses here. The only obvious similarity that all of them starts with 127. At this point, let's just note all this information. We have a bunch of hostnames, DNS requests, and IPs. Alright, next we can try the application itself. I will execute chess UI in my Ubuntu VM. You can see that it's really a chess program, and you can do steps, but whenever you do something, it's gonna say Deepflare has resigned. Deepflare is supposed to be the AI behind this chess game, and apparently something doesn't work right. And if you think a little bit about it, it's kind of obvious that what we see in the network traffic is that it communicates with some kind of server. And since we don't have this server running, whatever we do, the AI is not reachable, and that's why it always says that it resigns. We can open it now in IDA. We can look at both the executable and the library, but most of the interesting information is in the library, so that's what we are going to look at now. As we open it, we can see that there are some function names. That's already good because we don't have to guess them. From the first look of it, the most interesting function should be the getNextMove. It will get apparent pretty quickly that the point of this function is to figure out the next move. So when you do a step, the executable is going to call the getNextMove function from this library, and this function is going to figure out what should be the next move of the AI, so the chess program itself, and then make that step, and then wait for the user for his next move. In IDA, I've already changed some names and added some comments, so it might be a little different for you than what you see here. Here, there is some loading, there are some branches here, and then there's a longer branch here, and then it finishes. The next step should be to figure out what parameters this function gets. For that, I think the easiest way is to actually run the application in a debugger and check how the function is called. So I will go back to my Linux VM, close this one, and open up GDB. So I do GDB chess UI. I use the PIDA extension for GDB, which just makes GDB look somewhat nicer and provides a couple of extra features for reverse engineering. We can run the program, it loads up, and this is a screen generated by PIDA. That's the reason why I like it, because there's a bunch of information available right away. You don't have to print them manually. So I will put a breakpoint at the getNextMove function. I will continue, and I will make a move. And now what we want to figure out is which parameter is what. So just remember, in 64-bit architecture, the calling convention is that the first 6 parameters are passed through the registers RDI, RSA, RDX, RCX, R8, and R9, and the rest would be passed on the stack. First, we need to check these registers. So first, let's look into RDI. RDI contains 0. So this is something that we have to check later to figure out what it means. Then RSI holds a pointer to the string pawn. So this is where the figure name is passed. RDX is hex 11 and RCX is 13. So we can note this to ourselves and we'll see what's going to happen with them. R8 is a pointer to something. This wasn't really helpful. We found out a couple of things, but it's not super obvious yet. We can go back to IDA. I'm gonna kind of spoil the drama here because I already renamed the registers, but if they are already here, we can talk about it how I figured these out. As I showed, RDI is here, EDI is copied into a variable, and I called it step counter. If you remember, it was 0 at the beginning, but if you keep debugging as you make moves, you will see how it increases. Then we see that RSI holds the figure name, so that's pretty easy. RDX and RCX here only used the first 4 bytes, EDX and ECX. They contain the field coordinates, first where the step is coming from, and the second where it goes. For instance, in this case, we are stepping from C2 to C4. This is encoded in these two values. We are going to see that in a minute how I figured it out. And R8 contains what I called a return struct. It's basically a place where all the return values are stored. It's going to be very similar to what we sent to the server, so the figure name and then the from to positions. Here we see I call these functions create step as domain name. So let's see that in a debugger. In GDB with S, we are single stepping. Here we see as we proceed in the code, this is just initializing variables. And then there is a stack canary, which is an exploit protection technique, but it's not really important to us. And this is basically setting up the parameters for the function call, which is a string copy. That's not too interesting, so we can continue here down the road. Now we are setting up for another function call. ESI is holding 11 and RDI is holding a pointer. We can check out where it points to. So RDI points to the string pawn. Let's go into this function. We want to find out here what happens with RSI and RDI. We are setting up some variables. REX has now the word pawn, RSI has a dash, and RDI has the word pawn as well. Then we are calling stringcat, and the return value is in REX, and we just concatenated the string pawn with dash. All right, let's keep going. REX has 11 hex, which is the other input. We shift it to the right with 3, so it becomes 2. And end it with hex 7, which doesn't really do anything in this case. As we keep stepping, RDX is now 10, and continue stepping. We call stringcat again. It returns with pawn-c. So we added the first part of the square coordinate. Basically, we extracted out the letter C from the input parameter OX11. And now we continue with that. We end it with hex 7. And we are doing some black magic again, and we got 1. Setting up stringcat again, and we got pawn-c2. After that, we leave the function. So to summarize, the function had 2 inputs, pawn and hex 11, and we got the string pawn-c2. After this, we can continue, and the same function is called again, but with a different input. I think the best will be if we just let it run through and see the result. And we got pawn-c2-c4. Now we can assume that this function decodes the position coordinates from the second parameter and just concatenates it to the first parameter. It is called twice, and after that there is a reference to gameofthrones.flareon.com. This will be concatenated together with stringcat again. With that, we got the domain name that we saw in Wireshark. That's what we are setting up here. There is a get host by name, which will actually do the DNS resolution. The DNS request is going to go through the network, and it will return, hopefully, with a struct called hostend. After that, there is some magic, but the point is that we are checking the first byte of the IP address, whether it's 127. As you can remember, all the resolved IP addresses started with 127. After that, there are some other checks on the IP. We look at the last byte of the IP. First, I misunderstood this requirement. As you can see in the comment, it's still wrong. What it actually does, it checks whether the lower order bit of the last byte of the IP is 0. This mistake is going to have consequences later on. So these are the requirements that our IP has to comply with. There's another test here, and as you can see, when I wrote this comment, I still didn't know what it really was. What's happening here is that we take the third byte of the IP address, but only the lower 4 bits because we use AL. So if the IP is, for instance, 127, 150, 96, 1, then we check 96, which is an 8-bit number, but we are only interested in the first 4 bits. We end it with 15, which is OXOF. This zeroes out the upper half of EAX, so that only the lower half is analyzed further. Once I understood what's happening here, I called it a step counter. As I mentioned, if you would debug multiple turns of the getNextMove function, you would see that in each turn the step counter is increased. So this part of the IP acts like a serial number for the steps. Here we are checking that the step counter we got from the client when the function was called is the same that the one that was delivered from the server through the IP address. So this is basically making sure that the steps that the client is making is in sync with the steps that the server is sending back. And this is going to be interesting later on. And when all these are fine, then we go into the big block here where most of the magic happens. I won't go through it instruction by instruction, but I would like to point out a couple of interesting stuff. Here we can see some calculations being done. Let's see how we can figure out what happens here. There are 2 important locations in the binary. This part I renamed flag destination because it's a place in the binary where after 30 empty bytes, you can see the @flareon.com, which is supposed to be the end of the flag. So we are expecting the application to fill out the empty bytes to create the flag. You can find this place when you are reviewing the strings in the binary. So we definitely want to monitor what happens here. And the other location I call the encoded flag. It's a set of seemingly random bytes located in the binary with the other hard-coded strings. So let's go back to the code and figure out why I called it encoded flag. We take the step counter and double it. We use the resulting number as an index in the encoded flags array and load that value. So we take one hard-coded value and we take the second byte of the IP address. Below you can see that we XOR these values together. This is the equation I wrote in the comment. Flag I equals to counter times 2 character in the encoded flag array, XOR the second byte of the IP. After that, we copy the newly calculated value to the place I call the flag destination. But the function is not over. You see, it does another round of decoding, but now the counter times 2 plus 1 character of the encoded flag array. We XOR it with the part of the IP address that we've already seen. So basically what happens here is that every IP is used to decode 2 characters from the encoded flag array, and they are copied to the flag destination location. After that, there are a few more steps, I think, to recover the AI's next step from the IP, but that's not too interesting for us in regards to the flag. It will also return the message to the client to print. But I think we figured out the important part, and that's how the flag is decoded. So now I want to get the application working to be able to debug it properly. But unless the client gets responses to DNS requests, it will always just resign. We need to somehow imitate the AI and reply with valid DNS responses. Since we have the network capture, we can extract the data from there, and we can build an air quotes AI that can at least reply with the steps that are observed in the network capture. We are not going to be able to do different steps because we don't know the right moves for those, but we could use those that are already in the capture. So let's do that. We can extract the needed information from the PCAP with tshark. Tshark is a command line version of Wireshark. To extract the data we want, this is the tshark command I'm going to use. So tshark -r capture.pcap, and here this is the filter we want to use. We just want to see the DNS responses. We don't want to see the packages that contains the request, just responses, because those contain both the request, the domain name, and the resolved IP addresses. We can choose which field we want to extract. We want to get this DNS.a, which is the DNS answer, and that holds the IP address. We also need the DNS query name, which is going to hold the domain name that we are interested in. Since the localhost appeared in the results too many times, I just use set to remove all 127.0.0.1 from the results. Let's run this command. We get a nice list of IPs and then domain names. I use this information in the /etc/hosts file. You probably know that when a program wants to resolve a domain name, the first place the OS looks at is the /etc hosts file. If the domain name can be resolved from there, then it's not even going to send out the DNS request. This is just a simple stupid name to imitate the AI, because we don't actually need the DNS server or something else running on the network. We can just use the host file. Now we can do all these steps in the game and we will get a response, hopefully. So let's try it out. We can choose a working step, which is, for instance, pawn G2 to G3. I continue in the debugger. And Deepflare has resigned. So something is still missing. Now let's remember the requirements. The IP had to start with 127, that's fine. It couldn't end with 1, which is also fine. And there was also the step counter that had to match with the step counter in the client. So we need to do the steps in the correct order to make the AI work. But for that, we have to figure out the encoded step counter in these IP addresses. To do that, I wrote a script that I called calcorder.py. It opens the file dnsresp.txt and then goes through each line, takes the IP address and do the same calculations what we saw in IDA. It takes the third byte of the IP address and ends it with 15, like here. And it just prints the serial number, the IP address, and the host name. So let's see. Now you could see that we have all the IP addresses, and these are the step counters extracted from the IP addresses. I will also do a sort. Now this means that we need to make sure that we only use the appropriate steps for all step counters. So for instance, when I start a game, I cannot start with C6, D1, C1, because these are all 5th steps, or actually 6th because the counter starts with 0. Now we can try to play the game. And here comes the consequence of my mistake on the IP requirements. If I had remembered that the lower order bit of the lies byte of the IP must be 0, then I could have filtered this list further, which would have given me the straightforward solution. But I didn't, so I did it the hard way, which you will see now. Without that information, at this point, we have a couple of decisions to make at each step. And often we won't be able to do specific steps because the figures are not in the right place. For instance, we can start a game only with these steps because these have the step counter 0. King is on E1 at the beginning, so king E5 is not going to make sense. So if you look through it, it could be either bishop from F1 to D3 or pawn D2 to D4, etc. So when I solved this challenge, I pretty much went through it this way, every time trying to figure out which could be the valid step. And sometimes, and in some cases, there is only just one option. So it's not terribly complex, but it's kind of a brute force solution. Through trial and error, I came up with this list of working steps below. We can try it out. So start with D2 to D4. As you can see, it's stepping, and it's stepping because we have the hostname resolution in the etc/host file. And also the step we made is correct based on the available IP addresses. So that was the first one. Then C2 to C4, then B1 to C3. Then again, this is the point when you can debug the whole thing in GDB, because that's how you can track every step and look at how the values are changing. That's how I figured out most of the things that you could see in IDA. So which variable does what, which parameter is what, etc. I also figured out where the flag is stored this way. So let's see, I will just step through it. So E2 to E4, and as you can see, here at the bottom, we see the messages, what we have seen in the binary as well. Now I will break the application and put my breakpoints back and continue. All right, I was at E5 to E6, so queen D1 to H5. Yes, so the reason I stopped here is because this was my second mistake. I don't know why, maybe because of working on this in the middle of the night, I didn't find the correct last step. And I assumed that the guys at Flare intentionally gave a list of IPs that doesn't fully solve the challenge, which they didn't. But I figured I need to solve the last step some other way. All right, to figure out the rest, first we need to look at how far we are in solving the challenge. So I will try to find the flag destination in memory. So let's go back to GDB. If you remember, there was a sleep. Yeah, so this sleep call, that's when the flare is, air quotes, thinking. There is our sleep, and this is the address that's going to be interesting for us. I will put a breakpoint at this address and continue. All right, it stopped there. We can see right away that RAX points to a string. It says, looks like you looked up the whatever. Now we can do some more steps. We just copied one character into this memory address, and as you can see, the new character also appeared at the end of the string. If we continue stepping, you see we're extending this string. As you remember, we always decode 2 characters from every IP address. So this is going to be that second character. We are loading this string back again, and we are adding another byte. So up to here, this is the 15th step, and that brings us to this string. What we are missing is the last step, which is going to be 2 characters, and then add flareon.com to actually get our flag. If you remember, the empty space we saw in IDA was 15 bytes long, ending with @flareon.com. That's why we know that. One of my struggles was that I wrote a script that would put together all the possible string combinations for the IP addresses, and I would encode all of them with the hard-coded values in the binary to kind of try to brute force the flag and find a meaningful flag. This was more or less useless though, because I figured out how it is built in memory and I didn't really need it, and it took a long time to run. However, as a side effect, I had a code which I could easily use to encode and decode whatever values are encoded in the IP addresses. So basically I repurposed this code to figure out the last characters. I printed every IP that contains printable ASCII characters. You see them here. And my assumption was that since this is what we know so far, looks like that you looked up in a lookup. So I'm kind of expecting a P here at the end to get lookup. Because of that, I assume that the next character will be a P and one other character for the last 2 characters. So I was looking for an IP that has P as a first character. So I could have formatted this list somewhat better, but if you look through it, this is the IP that contains P as the first character. And the second character is a Z. This is the only IP that makes the flag meaningful. And it was actually the right flag, which is looks like you looked up in the lookups at flareon.com. So that's it, we got our flag. As I mentioned, this is a somewhat complicated solution due to my mistakes, but I thought that's life, so I would rather show you the mistakes as well, not just the final solution. Just to recap, we had this chess tool which asks an AI to get the next steps. The communication was in DNS, it sent a DNS request with the hostname which contained the steps it wants to make, and received an IP back. The information was encoded in the IP, there were some checks on the IP, and there was a step counter encoded in the IP which synchronized the client and the server. Using IDA Pro and GDB, we could figure out how the flag is calculated and where the encoded flag is stored in the binary. Then we extracted the domain names and IPs from the pcap file and used it as a host file to imitate the AI. And basically after that, we could actually make valid steps. And then we intuitively figured out the right steps from the list based on the step counters. However, the last 2 characters didn't work because the last step was incorrect. So for the last characters, we assume that the next character is going to be P, and we figured out that there is only one IP which contains P as a first character, and it also had Z as the second character. And these turn out to be the last 2 correct characters. Alright, this was a long one. Thank you for watching. If you like these Flareon challenges walkthroughs, I already have a couple of them, so check them out. Otherwise, like this video or subscribe to my channel. So I hope it was useful, and thanks for watching, and happy hacking. Bye.